we are going to talk about a heat transfer phenomenon. In this case, fine equation and finally long fin. The integrants are Elvis Viteri and Carlos Santana. Introduction. A fin is an extended surface that increases heat transfer. Two heat transfer modes are together, conduction and convection. Common in engineers, for example, car radiators, heat sinks, refrigeration systems. We have the description. First, fin equation comes from an energy balance where conduction competes with convection. Describes the temperature distribution along the fin. Infinity long fin. The tip temperature equate the ambient temperature is T equate T infinity. The temperature decreases exponentially along the fin. A theoretical simplification that helps engineers analyze heat transfer efficiently. Okay, relevant equation and general solution. The first equation shows the energy balance. Heat conduced in equate heat conduced out plus heat lost by convection. The different equation describes how temperatures change along the fin. The parameter M combines material and geometric effects like H, P, Q, and A. The solution gives the temperature profile for the infinitely long fine.
Hello, my name is Carlos Santana, and I am going to explain how to apply the boundary condition to the general solution for the infinitely long time equation that my partner found. Well, the general solution is the equation number one, and as we can see, it's composed by two functions of x. It's a linear combination of two functions of x, and the boundary conditions are presented in the equations two and three. For the first boundary condition, replace x equal to zero, and on the other boundary condition, replace x to for L, and L tends to infinity. So we if replace L x equal to L in the equation number one, obtain the equation number four. And if we analyze this equation, uh, we we see that we saw that the first term of this summatory is useless for us because when x tends to infinity, the first term tends to infinity. Uh, this behavior uh, is not expected. On the other hand, when x tends to infinity in the second term tends to zero, and the behavior is that we expect. And for that reason, only the second function will be considered in the final solution. Yes, in the final solution. The first boundary condition, x equal to zero, allows find the constant C2. So now we have a particular solution presented in the equation number seven, and have to replace M in the equation number seven, reorganizing and solving for T. That is the equation number eight. And now this expression allows calculating T at any position of X. And if we differentiate the function T, obtain the equation number nine. Now, here is a relation between the head conduction, the head of conduction in the base and the head of convection in the surface of the fin. This head is equal because the system is in a steady state. So R is in steady state. The question number 11 presents the form of head conduction for the law of Fourier. And if solve this equation, replace the derivative of the temperature in the expression for the head of conduction in the base, obtain the equation number 12. This is finally the infinitely long thin equation. Uh, Now we have a problem for understand better the concepts that I have explained. The problem is you have a rectangular aluminum fin in a cooling system. The fin is infinitely long and is exposed to a fluid with a heat transfer coefficient. You need to calculate the rate of the heat transfer from the base of the fin to the surrounding fluid. The data given are the thermal conductivity of the aluminum, that is 205 watts per meter Celsius degrees. The heat transfer coefficient, the perimeter of the fin, the cross-sectional area of the fin, the base temperature of the fin, and the fluid temperature. And the calculation is uh, first calculate M with the expression of the square root of the division of the heat transfer coefficient uh, multiplied by the perimeter, and this divided by the thermal conductivity and the cross-sectional area. We obtain a value of 2.19 meters to the minus 1, elevated to minus 1. And the second step is calculate the heat transfer rate Q. So we use the expression of the equation for the infinitely long fin that found in the found before. So substitute the values for the equation, and finally obtain that rate of heat the rate of heat transfer is 27. That's 18 watts. Well, that's all. Thank you very much.